Now that we've gone over the background of texture mapping and looked at it sort of somewhat abstractly, we're now going to look at how we actually carry out texture mapping, in particular within WebGL. One of the things we'll see is that turns out that most of the, almost essentially all of the WebGL texture mapping functions are exactly those that are in desktop OpenGL and have been carried through. Probably the only exceptions are that we can only do two-dimensional texture maps in WebGL, which is most of what you're probably going to want to do. We'll talk about how you assign texture coordinates, which is how we get around a lot of the mathematical issues that arose when we discussed it abstractly in the last couple of lectures, namely that we really don't have analytic functions that do the mapping between the various coordinate systems. So we'll talk a little bit about forming images that you can use for doing texture. We'll see that in multiple places. Today we'll see it by a very simple example of how you can write a little piece of code in JavaScript that will generate an image that can become a texture map. Or the one thing that WebGL does do that you don't have in desktop OpenGL is that we can use the standard image formats that are recognized by the browser to directly carry those images in as textures, in particular GIF images and JPEG images. Now we'll start off with a very basic approach that talks about a three-step process. Actually, we're going to look at some other steps a little bit later, probably the next lecture, that discuss a lot more detail about things that you can do to control textures more precisely. But the three basic things you have to do is, one, the texture. What is that image going to be? And we're either going to generate it by some code, or we'll read it in from someplace. But we'll have to make that into a texture map, and we'll look at one OpenGL WebGL function that does that. Actually, we don't even have to bother, I believe, to enable texturing in WebGL, but usually in the more general desktop OpenGL, you have to enable which texturing you want to do, 1D, 2D, 3D, 4D. Okay, the second part is assigning texture coordinates to the vertices. We're going to look at the texture coordinates as being another attribute, just as color could be assigned to a vertex and normal could be assigned to a vertex. We're going to now additionally say we can look at it as another vertex attribute and assign texture coordinates. And that's what's going to get us around the problem of not knowing these mappings analytically. And then there'll be a whole bunch of texture parameters that we can specify once the texture coordinates get out of the standard 0 to 1 range. How can we deal with some of the aliasing problems by applying various kinds of filters? And we'll look at those, and we'll look a lot more deeply at those issues in the next lecture. So here's a little picture of a texture map on a very simple case, because here we have a single quadrilateral and a texture image which is rectangular, and mapping that texture image to the surface is pretty straightforward, even though this texture may, this polygon may be tipped. It's still a flat two-dimensional surface, so you can see there's just a little rotation and scaling done to get this image onto that surface. So we'll start with this very simple case and see what happens when we go to more complex cases. Although what's always going to be the same, because we deal with polygons, is that we're going to always be mapping textures to polygons, in particular triangles. Okay, so here's a little example of that. Here's a little OpenGL's icon. It's a 256 by 256 image you can download off the web. We're taking just a piece of it here. It's being mapped to actually to a square, but that square is now being viewed in perspective. So when it's tipped with respect to the camera, part of it is closer to the camera than other parts of it, and so you see this scaling, perspective scaling happening. Okay, so that's what we're trying to get at. Okay, so let's look at it in terms of the pipeline. And as we said, last time, that there are two separate pipelines. The vertices are passing through the geometric pipeline, as are the texture coordinates, but the image itself is not part of what's going on in the geometric processing, what we're doing with the model view matrix, the projection matrix, and any other calculations we could be doing in the vertex shader. The time where we need the image is when we actually go to the fragment processor, and then we can use it as a way of helping forming or totally forming the color that's output from the fragment processor. So it's helpful to think of these two separate pipelines, although the Texel pipeline is generally fairly straightforward. All it's doing is taking this image and passing it on to the fragment processor. Now, how do we specify it? Well, here's the ways that we'll be looking at. The texture image, first of all, it's an array of picture elements which are called texels or texture elements, and we start off assuming that image is in the central processing unit's memory. It's on the application side, and what I have to do is get that over to the GPU, which generally will have a lot of texture memory attached to it that lives on the graphics card. So we can use an image in a standard format for WebGL. I think I have an example I'll show you that's using a GIF image, but it'll also recognize things like JPEG and probably PNG images. Or we can generate it, it'll have a simple example of doing it in the code. So let's assume there's an N by M image that's available. I probably should also mention that historically, texture mapping you were required to have images whose sizes were 2 to some power. So you could have a 512 by 512 or a 512 by 256. Recent versions of OpenGL have gotten rid of that restriction. If it's still a problem on some system you can always write a very short little piece of code that will take any sized image and scale it in some way to be a 2 to the n by a 2 to the m image. Okay. As we said, that there's WebGL only supports two-dimensional texture maps. It would be nice if it had 3D too. That'll probably happen in the next version. 1 through 4 are supported in desktop OpenGL. Okay, so here's the key function. It's one function that says what is my image that I'm going to give you, and what size it is, what format it is, all the things that the GPU needs to be able to deal with that image. So let's go over the parameters. The target has to be actually little GL texture. This is a slide I obviously copied from the last version. It's little GL dot texture underscore 2D. That's to allow for you also having in the future 1D, 3D, and possibly 4D textures. Level here has to do with MIP mapping, which we'll be talking about in a later lecture. MIP mapping is a way to get around some of the aliasing problems by having texture images at varying resolutions. So if I start with, say, a 1024 by 1024 image, I can also have a 512 by 512 version, a 256 by 256 version, and so on down to a 1 by 1 image. So one of the things that this does for you, and we'll see examples of that, is it allows you to use a smaller texture map when what you'll see on the screen is actually very small. So for example, if you start with a 1024 by 1024 image, but once you've done the viewing and the projection, that reduces to one pixel on the display. You don't want to have to be processing all those million texture elements. So having textures at different sizes allows the GPU to be much, much faster and much more efficient in handling the texture maps when visually you are probably not going to notice the difference. Okay, how many components and just how many elements are in a texel? Generally, it's going to be RGB or RGBA. You're going to have to specify the width and the height of the image. Border is not used anymore. It was used to allow for some problems that had that occur when you get to the edges when you're trying to do anti-aliasing, and generally you could have an extra 1 pixel wide texels along the top, bottom, right, and left, but that's been deprecated. And then we have to describe what those texels look like, whether they're generally we're going to say they're something like unsigned bytes, which is actually what we're going to have to use for WebGL or some other format, and whether they're RGB or RGBA. And finally, the key thing here is a pointer to the array on the application side of where those texels actually are. So here would be a typical call. The only thing is I forgot to change these to little GL dot and little GL dot here, but this is the standard call. 0 here means that this is the top level of the MIPMAP, the largest one of the family of textures you're using for that image, or that you're not going to use MIP mapping, so you have level 0. This would be saying it's a 3-dimensional, 3 components, 512 by 512. Forget about the border by putting a 0 here, and then it's an RGB image using unsigned bytes, and this would be the array that they're stored in. So here's a really simple little example, but it's very helpful. We'll display that in a little bit, of generating a checkerboard image. Checkerboard images are nice because they allow you to really look at the aliasing kinds of issues, because you'll have nice, well-defined little blocks that you can make bigger and smaller and see how they're actually rendered. So this is a little bit of code. This is the sort of the very straightforward way to do it, to get an 8x8 checkerboard within a text size by text size array. You can actually replace the above code by this one little, sort of C-like line that uses some of the bitwise operations to do it. It's a little harder to understand than what's going here. So you're either setting things equal to black or white, and it'll turn out to be an 8x8 image inside of that. Or if you change C here, you can make it any color you want plus white in that checkerboard. And now you have an image. Also note that what we're doing here is putting the entire image into a 1-dimensional array, because that's what we really have to pass around in WebGL to make this work. You could define it as a 2-dimensional array, but eventually you're going to have to do the equivalent of flatten and convert it into a long 1-dimensional array. So in this example, I just made it a 1-dimensional array of text size by text size, but there's RGBA components here. We're always setting the A component to be 255, which means that it's opaque. Okay, so fairly straightforward way of doing it. If you instead want to use a standard image, then you can simply do this. This would be specifying it totally within the JavaScript file. You say, so on load, we're going to have a function that sets up all the texture parameters. We're going to get to that in a bit. But then we're going to say, okay, well, the image source for that image. So we say, okay, I'm going to have a new image. Image is an object that's recognized by JavaScript, and that the source for that image is going to be this file. And I have an example of that I'll show you that's on the website. You can also do it, which would be more consistent with the approach that we've taken, is to have that image defined within the HTML file rather than the JavaScript file. So you can use the image tag, give it an ID, which you can refer to back in the JavaScript code. The source is again that file for that image. It's an image we used for a SIGGRAPH conference. Use that tag, refer to that ID back in the JavaScript file, and say that the images use the get element by ID from TechImage, which will now bring you back this image, and then do exactly the same thing. Configure the texture and set its parameters up as we'll be seeing. Okay. Now the part we have to add is how we define the texture coordinate. So here's a very simple example let's assume we have a texture image, and even though this is a discrete image that might be, 512 by 512 or any other size, we're going to assume it's continuous. And by convention, the values are called the S&T values, and they're going to both range over the values 0 to 1. Now, here's a little polygon, a triangle, and what we have to do now is somehow map a part of this texture image over to this image. So if I was to look at that in terms of the mapping, they'd say this triangle corresponds to some triangle in texture space, and I have to define that mapping. Well, one way I can do that is to say assign to each of these vertices, which will have a location in XYZ space, assign it a value in the texture space. So for example, if you follow this lower left corner of the triangle, if I assign it texture coordinates 0.4, 0.2, I'm assigning it this value over here in the blue space, where little b that you can see here. Likewise, if I assign the vertex C 0.8, 0.4, it corresponds to this point over here in the green space, and likewise if I assign ST to 0.2, 0.8 over in texture space, that corresponds to this little a over here. So that's defining a triangle in texture space, and that triangle is being mapped to this triangle inside the rasterizer. So this is what makes the whole thing work, is once you've assigned texture coordinates to the vertices, you can pass those values on like any other attribute to the rasterizer, and the rasterizer is going to do the interpolation to find what the texture coordinates are for each fragment that it's generating as it rasterizes this triangle. So it's a very, very straightforward process, but assumes that you know what texture coordinates you want to assign to the vertices of the triangle or any other object that you're working with in XYZ space. So that's really sort of burying the problem and says, well, I'm leaving it to the application to know what this mapping function is, and I just happen to pick some arbitrary values for this example. But it makes the whole process work very, very rapidly within the geometric pipeline, because the geometric pipeline is doing this interpolation. And notice that by interpolating the texture coordinates, I still don't really have to deal with the texture until I get to the fragment shader, because all I'm doing is mapping these vertex values, which are not the values of the texture, which are RGB or RGBA values. So here's a simple example with a cube. I'll show you that in a minute displayed. And the point here is first that we're assigning texture coordinates to 4 vertices. So I'm going to actually map to the cube, and for each face of the cube, that same cube example we've been using, I'm going to assign texture coordinates to the 4 vertices of each square face, and each square face will then, as before, get broken up into 2 triangles. And so I'll use the 4 corners of the texture map, 0, 0, 0, 1, 1, 1, and 1, 0. I'll just store them in an array text coordinate. Now if I look at the quad function, this is the beginning of the same quad function that we've been using all along, and the only thing I'm changing here is to assign to add an array text coord and coordinate array, and what I'm going to do is now push the values of the texture coordinates onto that array. So here I assign, I'm pushing the location of the vertex A, I'm pushing the color of vertex A onto the color array, and here I'm deciding I'm going to use text coordinate 0, 0, 0 for A, I'm going to use text coordinate 1, 0, 1 for vertex B, and so on for the other vertices, as I define either a pair of triangles or a triangle strip or a triangle fan. We've seen all 3 examples. So again, the point here is just that by adding this one extra attribute, text coordinate, I've added what I need to do texture mapping within the application, and now I'll just add the image as we did before. Okay, so repeating how the interpolation gets done is that's done by the rasterizer, just as with any other attribute we pass. Now, one of the things you have to be careful of, is, as I started to point out before, is that it's leaving the problem to you to assign the texture coordinates. And if you assign them well, you'll get some nice mapping. So here's a little checkerboard, and by assigning this mapping, I can get this, or I assigning the texture coordinates a little bit differently, I can get this, and I'm saying, well, that's a poor selection because this one nicely lines up with, at least with this axis. This one distorts that texture pattern. And it could be even worse when you start dealing with multiple triangles, because I have to, and this would be the problem even in a variant of desktop OpenGL that supports polygons, because internally those polygons are being tessellated into triangles, and when I do that, I can get all kinds of distortions of the texture. So here I've assigned to a quad texture coordinates to the four corners, but because we've had to break up, or the hardware has broken up that quad into, or that trapezoid into two triangles, the texture coordinates get broken up and interpolated separately over these two triangles, and I get this bizarreness of how the texture is mapped. And so you're always open to that happening, and you have to be very careful in how you assign the texture coordinates. That's the reason I want to point out these checkerboard textures are very, very helpful for trying to learn how these mappings are actually done. So let me look at a couple of simple examples to end this lecture, and we'll talk about more of the detail in the next lecture. So let's look at this. So let me go here. I don't want to look at this one. This is next lectures. Let me look at this one here. Okay, so here's what's on the website, and you can get to these yourself. So if you look at text coordinate cube 1, this thing is taking this image. Here's the texture image that we're mapping, and I'm mapping it to each side of the cube. Now I haven't looked at the fragment shader yet. We'll do that a little bit later, but notice that what I'm doing here is that I'm using both the color that I assigned as a color attribute and the texture that I put in as this texture image, combining them to form the image. Here I think I'm just multiplying the two together. And the point again here is that you can do whatever you want within the fragment shader. You can have this texture totally determine the color on each face of the cube, or you can have it being combined with a color that you either assign as a vertex attribute or even as a uniform variable, or you can even do a lighting calculation and combine this texture image with the result of a lighting calculation. So if you did that, then what would happen is that it would be sort of similar to having say a painting on top of an image or on top of an object, and that object then would be lit, and so you would see both phenomena going on at the same time. So here's just using a GIF image in this case. If I go back here, let's see, texture cube 2. Now you're seeing here an example. This is the 8x8 checkerboard being used as an image. You don't see the aliasing here. You're going to show you aliasing more in the next example because the resolution is pretty good. You might see a little bit of jackiness as this thing rotates. So in this case, the color is totally, no, actually it's both, because the color is being determined by both the texture map, which is black and white, and the underlying colors that I assigned to the cube as I did before. We use the red, green, blue, cyan, magenta, and yellow to color this cube, and now I'm placing that texture essentially on top, or looking at the texture image, the checkerboard, as being some kind of a mask that determines whether the color shows through or doesn't show through. So again, these examples are on the website, and I encourage you to play around with them, especially to play around with the fragment shaders, because that's where the action is really happening. And actually, for a learning experience, play around a bit with the texture coordinates. If you change the texture coordinates in the JavaScript file, you'll see some very interesting effects occurring here. And as I said, next lecture, we'll talk more about the detail involved in texture mapping.